Okay, so we have already introduced you to one circuit called the half adder while discussing about comparators, and now we are going to look into a little bit more useful adder, because half adder is primarily going to just add 2 bits and not consider anything as an input carry or right. So we need something which is more than a half adder, and that takes into account that carries that get carried over if you want to add 2 multi-bit numbers, right. So in order to add 2 multi-bit numbers, we typically use this functionality or the logical building block, which is again a combinational logic building block called the half adder. So if you consider these 2 multi-bit numbers, these are n-bit numbers which is represented by A, and as I told you, as a convention we are typically going to stick to A0 or A0, and that 0th position typically indicates the least significant bit, right. So this is a convention unless unless otherwise mentioned, right. There you could come across some books or some examples where n is denotes the least significant bit, but typically this is the convention, right. So and the first one is an n-bit number which is A, and the second number is B, okay, and we want to simply add them, right. And this is very similar to the kind of additions that you have done in your junior school, right. Once you want to add 2 decimal numbers, you typically start from the right and add them and make your way towards the left, right, which is from a position of least significance like units location, then you move on to the tens location, then you move on to the hundreds location, and so on. Here we are trying to go from this is a binary system of base 2. So we start from the least significant bit, here it is A0, and slowly move on to the left hand side, right. This is the right hand side, this is the right hand side, that is why we mentioned from the right to the left, and one column at a time. What is meant by one column at a time is you want to add 2 bits belonging to a given bit position. So this is a, let's say this is AI, right, AI and BI, which is I equal to n minus 2. This is a given bit position which is referred to as a column, right. So that is why we have written here one column at a time, okay. And there is one more thing to it, one sum and one carry bit. So once we add 2 bits, for example, if you add 2 digits, right, which is basically a decimal equivalent of a bit, that could go from 0 to 9. Similarly here it can be 0 and 1. So if it is 0 to 9, if you add 2 of them, it is going to create a sum, and there could be some leftover, right. If it is more than 10, there will be a units location, the tens location that you need to also consider, right. So for example, if you add 5 and 7, the units location, the sum we typically call it as, here it will be 2, right, although the sum is 12, but 1, that is the carry, is moved on to the left hand side for the next significant bit position, right. Here it will be the next significant decimal position. So from units position we want to move on to the tens position and put 1, okay. So we replicate the exact same idea of decimal addition in the binary form also. So here if we add 2 bits, and 2 bits could only have 4 combinations. I think this is something that we have discussed while discussing about half adders, while having the discussion on comparators. There you can have only this possibility. So if you want to do A and B, right, sorry, A plus B, don't think of this as an OR operation, you are actually trying to add them, right, in the summation context. So A and B could only be 0 0 0 1 1 0 and 1 1. These are the only possibilities, and this will give rise to a sum, and it will also give rise to a carry. So let me not use this plus anymore here. So you will have a sum, and you are going to also have a carry if there is an output carry that is going to be coming out from the sum, right. That could not be held inside the least significant bit position. So here if you see 0 0, the sum is going to be 0, there is of course no carry. 0 and 1, it sums to 1. Even if you convert it into the decimal form, it will be the same. 0 means 0, 1 means 1, right? Just that you do not have any meaning to 2, right? You cannot write the number 2. 2 has to be represented again to using 2 bits. Okay. So here we are trying to do single bit addition. A is a single bit, B is a single bit. A plus B here, sum is again 1, carry is 0. Here also the sum is 1, the carry is 0. 1 plus 1, the number is going to be 2, but we do not have a 2 in the binary system, right? It only allows for 2 bits. So 2 is going to be represented by 0 in the least significant bit and 1 in the second most least significant bit, which is the which is basically 1 0, right? So the sum is going to be 0, the carry is going to be 1. Okay. So while discussing the half adder, we spoke about this function. This could be represented by the XOR function, right, which is equivalent to computing the sum of these 2 bits. Okay. And carry, if you can see that all of the carry rows are 0 except when A and B are simultaneously 1, right. So if C is 1, that means A and B has to be simultaneously 1, which basically means that A and B has to be ANDed, right. It's just the mean term. Even if you look at the mean terms, we are only going to pick up the mean term for C, and which is 1, which is nothing but AB, right. So this mean term is AB. Okay. So C is going to be AB, and the what is it called, the sum here is going to be A bar B plus A into B bar. So these are the 2 mean terms that are here, A bar B and A B bar. So this is how you compute the sum of these 2 bits. But often when you have a multi digit addition or multi bit addition, right, it's not that it's a 1 digit plus 1 digit you give rise to 2 digits, right. For example, 9 plus 9 maximum you get is 18, right. But suppose you want to do, let's say, 21 plus 39 or something like that, right, your sum can be well above 18. Okay. 9 plus 9, the maximum number you can create is 18. Similarly here, if you have 1 and 1 2, the maximum that you can get is 1 0. Okay. But you are going to represent any number, when that is being represented in the binary form, it can contain many bits, right, depending on the format that we have agreed upon. It could be a 4-bit number, it could be a 5-bit number. That is the operation that we have to kind of create the hardware circuit for adding 2 8-bit numbers or 2 16-bit numbers, because this is a very important operation that takes place inside the CPU. The CPU could be a 8-bit CPU or a 32-bit CPU, which means that it is going to add 2 32-bit numbers, and we want to have a full adder that can add 2 32-bit numbers. Okay. So we start from the Lego block that I have already talked about, is about the half adder, which takes 2 bits and compute the sum and carry. Here, if you see the figure on the right hand side, I have A naught and B naught, which definitely you implement it using a half adder. It gives you S0 or S naught, which is a sum, right. But where is the carry going to go? The carry is going to be carried over to the next significant bit, because next I want to add A1 and B1. This is very similar to the decimal addition that we have done in our childhood, that A1 and B1 has to be added, but you also need to take the carry forwarded from the lower significant bits position. Okay. So here in this case, the carry could be 0 or 1. There might not be any carry at all, or there can be a carry which is equal to 1, and carry is equal to 1 is only going to be created if A0 and B0, in this case there is no input carry to A0 B0. A0 B0, if both of them are 1, then only you are going to create a carry. Okay. Or in the next case, in this particular column, so that is why we said we want to do the sum and carry, so one column at a time, because unless and until you do one column at a time, we do not know that there could be an input carry from the previous stage, right? So A0 and B0, only if I do A0 plus B0, I will know whether C1 is equal to 0 or not, right? Because C1, if it is 1, then the answer is going to change. If C1 is equal to 0, probably it doesn't matter. But in order to know that C1 is equal to 1 or 0, the next significant bit position addition has to be done first. Okay. So often I will come up with more details on this kind of circuits. It is called a ripple carry adder or ripple carry addition. This carry is rippled like a wave, right? The carry will start from the 0th position. It is going to be rippling to the first position, rippling to the second position, dot dot dot, right? So here in the first bit, like 0th, if I call it 0th, this one is the first bit position. A1 plus B1 is not enough. You have to do A1 plus B1 plus C1, right? And then look at the sum. So what's the maximum value that A1, B1, C1 they can take? A1 can be 1, right? It cannot be more than 1. B1 is another bit, it cannot be more than 1. C1 is another bit, it cannot be more than 1. So A1 plus B1 plus C1 cannot be more than 3, which basically means 1, 1 in the binary form. Okay. So it could be 0, it could be 1, it could be 2, it could be 3. Only if you have 2 or 3, then only the next carry propagation is going to be 1, because so if I write, let's say some AI plus BI plus CI, all of them are bits, right? So the minimum value could be 0, right? It could be 0, of course it could be 1, it could be 2, it could be 3, right? 1 plus 1 plus 1 is 3, right? So only if it is 2 or 3, then only you are going to have a carry that is going to be forwarded to the next stage. Okay. So 2 could be represented by 1 0 and 3 would be represented by 1 1. You can see that the units position here I am not looking at, the next position it's 1, right? So this 1 is going to be carried forward to the next one, right? A I plus 1, B I plus 1 and C I plus 1. So C I plus 1 is going to be 1. Okay. Whereas if the sum becomes 0 or 1, it doesn't matter. 0 0 0 1, there is no so C I plus 1 is equal to 0. Here C I plus 1 is equal to 1. So here if I come back, S1 is going to be the sum and the carry is going to be generated from depending on the values of A, B and C. So now what we have to do is we need to create a circuit for this, right? Earlier I have shown you a very simple example where A, B, S, C we have. So you can simplify sum as A XOR B, which is A naught B plus A B naught, not in the sense complement, A complement B plus A B complement, and carry is equal to A B. But here we have three things. We have A, we have B, as well as there is an input carry which is coming from the previous stage, right? So one way to approach this problem is the standard thing that we taught, which is write down the different possible combinations of inputs and outputs in form of a truth table, right? And that is what we would try to do, truth table of binary addition on one column of bits, right? Let me rub this for clarity. Truth table of binary addition on one column of bits within two n-bit operands. Okay. So if you are adding two n-bit operands A and B, they are both n bits, they are called operands, right? Operation is addition, operand is basically the data on which you are executing the operation, and they are n bits, and we have to choose one column and try to see that what is the truth table of adding those one column of bits. Okay, one column is a specific column that I have marked, right? Let's say A1 is one specific column of bits. Okay. So AI, BI are the two operand bits, and carry is the carry forwarded from the AI minus 1th stage. So the carry, as I told you earlier, is going to be forwarded to the I plus 1th stage, and the sum is basically the sum that is going to be associated with that column. Okay. And there are three possible inputs here. So you can only have three variables. So you can have 8 possible different combinations of inputs, right? So we just mechanically write them down, that A and B for every combination of A and B, we can have either carry equal to 0 or carry equal to 1, right. So, we have 4 combinations of A and B, and for carry equal to 0, we have 4 combinations of A and B, and for carry equal to 1, we have 4 combinations of A and B. And just logically we can figure out the sums and the carries. I will anyway go over it. So, if you see A 0 and B 0, carry is also 0, 0 plus 0 plus 0 is 0, right. So, the sum is 0, the carry is also 0. So, if you see 0 plus 0 plus 1 is 1, right. So, 1 is 1 in the sums place, but there is not yet carry, unless or until it is 2 or 3, I do not have a carry, right. So, 0 plus 1 plus 0, again it is the same thing, 1 is the sum, 0 is carry. Here if you see 0 plus 1 makes it 2, right. I cannot represent 2 by a single bit, 2 is a 2, it has to be expressed in 2 bits, 1 0. So, the sum becomes 0, carry becomes 1. Similarly, here there is only 1 bit addition, so 1 plus 0 0 is 1, so carry is 0, sum is 1. Here also it is 2, there is 1 plus 0 plus 1 2, so carry is 1, sum is 0. Here is the same thing. If it is 3, the example that I showed you earlier, 1 plus 1 plus 1 is the maximum value that could be taken by A plus B plus C, that cannot go to 4, right, because you are adding 3 1 bit numbers, it cannot go to 4 by definition. So, 1 plus 1 plus 1 is 3, carry is 1 and the sum is also 1, the sum bit is 1 and the carry bit is, the forward carry bit is 1. So, now if I ask you to come up with a circuit for this, that should be doable, right. You all know how to convert this particular truth table to a circuit. All you have to do is look at the, let us say I want to design the circuit for sum Si, and Si has to be expressed as a function of Ai, Bi and Ci. So, all you have to do, you have to choose the mean terms where and by the way, you should practice this, because do not leave it here, ideally you should go ahead and create the circuit. I am marking the entries that have 1. So, you can see that first one is, let us say A bar, B bar and C. Next one is, so this is A bar, B bar and C. The next one is A bar, B, C bar. The third one is A, B bar, C bar, and the fourth one is A, B, C, right. One thing you can simply do is that add them up, right, and using the Boolean algebra axioms that you already know, you can simplify them to a more compact form, right. That is one thing that I have already taught, right. So, this I should leave you as an exercise. You should actually create the circuit and see whether it could be further simplified or not, okay. So, if you do the exercise, you will see that we get something which is an XOR of these multiple bits, right. So, for a half adder, we had said that sum is equal to A XOR B. So, this operation, as I told you earlier, is an XOR operation. So, A is often written as XOR is like this, A XOR B, okay. The sum for the full adder could be written as A XOR B XOR C, okay. That but I would request you to derive this, because you know what is the formulation for an XOR function. So, the formulation for XOR function is, if there are two things, right, A and B, this is the formulation for XOR. So, once you have this as one unit, you have to then do XOR C, right. So, you have to expand A XOR B, use that as a unit expression, and when you take a complement, you have to apply, of course, De Morgan's law and all these things to get to the stage that where it is going to be the sum of these mean terms, okay. And if you look at carry, right, how do you compute the circuit or the expression for carry? The expression for carry again is the sum of the mean terms that I am marking using green color, those are 1, okay. So, you can always see that what constitutes of carry equal to 1 is here is A bar B C, A B bar C, A B C bar and A B C, okay. Again you can simplify them and kind of see that what's the expression that you are getting. Okay, and this is what I would say for any circuit. I mean, here full adder is just more we are doing for kind of logical completeness, because we are trying to build an ALU further down the line. But this full adder design should not be seen as anything very specific, right? Any circuit, if you are given some kind of an operation, how it should work, from the truth table you should be able to come to the design, right? That's the main goal of the course, rather than knowing that as full adder is A XOR B XOR C, because anybody can memorize that, right? What you need to know from a design perspective is that the exercise that we did just now, right? Given this is the operation, the way you should come up with a truth table and simplify them and come up with a appropriate circuit for that. Okay, that's the necessary takeaway that should be done by the students. Okay, so 1 bit full adder, and this is how the thing is going to look like. So we discussed the circuit. You have to just replace whatever circuit we have discussed within this black box. Okay, and if you see, often we will need a multi-bit adder, right? Because the operands, as I told you, is not going to be just 1 bit, right? It's not a 1 bit full adder. It is going to, you want to create a block that is going to create a, that is going to add to 32-bit numbers or to 16-bit numbers. So in that case, you need to just link together all these full adders in series, right? Typically called, I mean, this is called a cascading. Okay, so you have a full adder. The first one, this is the least significant bit, where you have A0 B0, because you start the sum without any additional carry, because there is no carry when you start in the units place. That's why the input carry C0 is equal to 0, right? I have to give this to make the circuit complete, because full adders expect 3 inputs. In this case, your input is going to be 0. You add S0, what you get is, if you add A0 B0, you get S0 and the output is C1. This is your forward, like feed kind of, feed forward carry. Okay, so as you can see that S1 is only going to be, this is kind of important to understand, S1 is kind of, is only going to be computed only when S0 has been computed. S0 and C1 has to be computed. Unless and until C1 is computed, S1 is not deterministic, right? Because you can always have A1 and B1 as, there's a 0 and 0, but C1 could be now 1, right? Then S1 should change. Okay, not only that, you will not also know anything about C2 unless and until this operation in the full adder takes place. Okay, so you can see that there is a dependency once we go from the right hand side to the left hand side. Okay, so I will write with an arrow that there is a inherent dependency, because the carry is going to be dependent on the previous stage, and carry influences, can influence the next carry as well as the sum. Okay, so you need to understand that to get the full adder to compute 2 n-bit numbers, it has to go through this n stages of full adders. Okay, and this is going to introduce some kind of a latency. So latency means delay. So suppose if you have a latency of delta time units of time, right? Let's say delta microsecond or delta nanosecond for a particular adder. This delta nanosecond is going to be repeated for all the different full adders, and they cannot be running in parallel for this architecture, right? This is called a ripple carry adder or a cascading carry adder. Ripple carry is more common. Ripple carry adder. So as you can see, the delay that you are going to get at the end of the day is proportional to the number of adder units that you have or the size of the operands. Suppose you have a 32-bit adder, you have to have 32 small full adders. Okay, so everybody is going to take this delta nanoseconds and so on. Here also delta nanosecond. For a 4-bit adder, you are going to have a total latency or delay of 4 delta nanoseconds. Okay. So why I am bringing up this thing is because the aim of an ALU, right, the arithmetic and logical unit that we are going to study as a part of the organization, they need to compute fast, right? Everybody understands the computer needs to be fast by some means. We don't know how, but somehow we want to make the computer faster. And for making the computer faster, these individual instructions has to run faster. So if you look at the instructions that execute in a computer, one of the fundamental instructions that is supported in hardware is addition, right? You can always say add a comma b, okay, and this is completely implemented on the processor in hardware. So add a comma b's latency is going to impact how a program, right, a program typically involves a lot of additions or let's say multiplications and so on, which is often executed by the full adder circuit, and if that is becoming the bottleneck, the program's bottleneck will be kind of dictated by the design of the adder. Okay. So if we have time, we are going to also look into things like how these adders could be made faster. There are things like called, I'm just going to give you the names but not going into the details right now, called, let's say, carry look ahead adders. Okay. So why carry has to be looked ahead? Because if I somehow magically knew that what is this C2 going to be, then I could have started with S2, right? But what the bottleneck here was, unless and until I know C1 and unless and until I know S1, I cannot find out C2, right? I need A1, I need B1, I need C1, then only I can find out C2 and S1. Okay, there is a dependency which makes it slower. This particular architecture is called triple carry adder, but there are some tricky ways to somehow cut down the cost, okay, to kind of make it a little bit more smarter, such that the latency is not n into delta, but it actually gets reduced. We are going to look into some more smarter adder architectures later. Okay. So the next thing is another kind of a circuit which is a little bit more generic compared to what we have studied so far, that was specific combinational logic blocks. Okay. So a programmable logic array is somehow can implement any logic function we wish to construct, right? And this does by interconnecting a set of min terms. Okay. So it's an array of AND gates followed by an array of OR gates. This is how you can think of, because this is very similar to what a sum of products does. Okay, because sum of products, if you even think of a decoder output, it is going to give you all the different possible min terms, right? It is going to give you just all the 2 to the power n different possibilities. And here also we are trying to have this AND gate layer, which is going to create all the possible min terms. Okay. And why the OR gate? You know that we have sum of products, right? Product is the thing that is realized by the AND gate, whereas the sum is the thing that is being realized by the OR gate. That's why we have an array of AND gates followed by an array of OR gates. You can always do the other way around. You can always come up with a product of some expression and flip it around. Okay. So how do we determine the number of AND gates? The number of AND gates is determined by the number of possible min terms in the system, right? Given the number of variables that we want to work on, you can always come up with how many min terms are required. For an n-bit logic function, we need a programmable logic array with 2 to the power n n input AND gates. Why n input? Because there are n terms, right? So either in terms of complement or not complement, they are ANDed, right? So just to give you an example, if you have A, B and C, you can either have A or A complement, A or A bar, dot B or B bar, dot C or C bar. So it can either be A, B, C, or it can be A, B bar, C and so on. Okay. So, you need here you actually need a 3 input AND gate that basically takes A, B and C and computes the ANDed version. You can always do the multi-layer or two, like if you are restricting that we cannot use multi-input AND gate, we have to only restrict ourselves to 2 input AND gates. In that case, you can always do ABC as A and B, that is being separately ANDed, and then you have C which gets ANDed one more time, and then you get ABC. Here it is A, here is B and C. But in case you want to, you do not have, you want to restrict the hardware specifications, because typically what happens is if you have too many inputs associated with a gate, there is a limit to it, typically called fan in. Okay, this is not something that you have to go into details, but fan in or fan out, which is how many components is being driven by the output. Fan in is that how many inputs are coming to your system. They have a limit because of capacitive effects and so on. If you have too many of them, then the circuit might become slow and does not kind of correspond or does not follow the timing specifications of the circuit. Okay. So, often we have a restriction. We might ask you a question that I don't like to have 8 input AND gates or 10 input AND gates. Can you simplify it? I can only support up to 3 input AND gates. You may have to do some kind of a simplification. And what's the cost of the simplification that you are paying? The cost of the simplification is the added delay. Earlier it was only a 1 gate delay. Here in this case you are going to have 2 gate delays. Okay. The slight nuance, right? 3 input AND gates might be slower than a 2 input AND gate, but in general if you say that how many gates get passed here there are 2 layers of gates in case of this design. Okay. So, programmable logic array is how you interconnect these mean terms and how you join them to create an OR of them, right. By definition they can create any circuit. Okay. So, that is what we do. We determine the number of OR gates, the number of columns in the truth table, because if you have multiple outputs, you will have multiple columns in the truth table. Okay. So, the AND gates will be determined by the number of inputs in the truth table, which is if you have number of variables as n 2 to the power n, and the number of OR gates is basically the number of outputs that you have, which is going to be evident from the truth table. So, how do you implement a logical function? Connect the output of an AND gate to the input of the OR gate if the corresponding mean term is included in the SOP. It is very straightforward. We have looked into it many number of times. You scan the truth table, wherever you find there is an existence of 1, you pick up that particular mean term and feed that particular mean term to the corresponding output, right, and the corresponding output is going to be the output of the OR gate. So, what is meant by programming of a PLA? We can program the connections from the AND gate outputs to the OR gate inputs to implement a desired logic function. It is not something that somebody is going to physically touch this hardware and do this wiring. This could be automated by means of programming, right. So, again we are not going to talk about things like hardware description languages, but as a matter of this discussion I can give you a slight detour. We have certain things called, just that you have a C program or a Python program which tells you that how a program has to be executed, right. You have a set of, after compilation you are going to have a set of instructions that get executed by the computer one by one. Here you are writing a program which does not directly gets executed per se, right. That program describes a hardware. Okay. And how can you describe a hardware? You can only describe a hardware in terms of the interconnections that you have in between the AND layer and the OR layer. So, this is your AND layer and this is your OR layer. Okay, this is output 1, this could be output 2, this could be output 3 and so on, right. This could be a sum, this could be a carry and so on. So, programming the PLA is going to we typically do it in terms of a class of programming language called HDL or hardware description language. It essentially describes that, okay, these are the variables, then you have to group this kind of inputs, you put them into some AND function or whatever and put it out in the OR gate, right? So this entire thing, once you synthesize a design, this is called synthesis, and put it in a PLA becomes a multiplexer. Once you put a design for an adder, a PLA becomes an adder. It's actually a generic circuit that has all these AND gates and OR gates. Given any function, it basically is realized in hardware. What the hardware will do magically, it will actually create some connections like this. Maybe you just need this min term, this min term, this min term, this min term and this min term and nothing else. So this will be floating. Okay. So tomorrow you want one more function, you don't like this anymore, you want to test out something else, right? So you will write the program, the hardware description language one more time and burn it on the same piece of silicon, same piece of hardware, right? It is just not going to be this anymore. Okay, it will be something else. Let's say this and maybe this, right, for this output. Okay. So the greatest strength of this programmable logic arrays is these are reconfigurable. Okay. Typically what happens in application specific ICs and so on, like entire hardware is typically in one IC, right? This is something that I was discussing while we kind of broke apart a Pixel phone and saw what are the different components inside it. We actually hit an IC very easily, right? And an IC is something that has already been manufactured and baked, right? So you have a function that is already engraved, right, in the IC. You cannot have a different functionality for the IC anymore. It has been done, right? So you can run as many times as you feel like, but you cannot reconfigure it. Whereas a PLA could be reconfigured as many number of times, although this has been done, right? The wafer has been made, but the interconnections are reconfigurable. Although you have a set of AND gates and a set of OR gates, but the connections in between them could change based on the way we kind of want to synthesize it. And that synthesis is done using this hardware description language. I can give you some examples, right? Hardware description language is Verilog is one kind of hardware description language. VHDL, right? This is another. This is equivalent to your C, C++, Python, Java, right? Those are something that are high level compiled codes that could execute on a processor. Okay, this is completely different. Hardware description language is typically used to describe hardware. Once you synthesize the design, the hardware changes its shape and size, whatever. Okay, to the extent that you can actually emulate a complete processor. You can write an HDL code and given a PLA, you can have a complete processor running. You can have a complete Wi-Fi network card running, right? So because all of them are actually some kind of logical blocks glued together. So if you have huge number of AND gates, huge number of OR gates, or basically the logical gate bank, depending on the number of gates that you have in the system, you can realize enormously complex functions. So one of the real example is an FPGA. So whatever I was describing here, Verilog, VHDL and hardware description language, these are typically used to program an FPGA. Okay, so FPGA stands for Field Programmable Gate Array. Okay, so again, it's an array of gates. You have maybe millions of gates in an FPGA, right, which could be used to realize any kind of a logical functionality that you require. Okay, again, FPGA is reconfigurable. Don't think that FPGA is one time. Every time you write a different kind of hardware, that hardware becomes takes a new shape, right? It's like a chameleon. Okay, don't think that FPGA is a processor that executes your HDL code. No. Okay, so this is something that you should keep in your mind, because reconfigurable hardware is a very important step in which computer systems are typically debugged before you actually create a full-fledged hardware that you tape out, right? Tape out means you actually send it to the industry, they actually print the or create the wafer, right? And that is that cannot be changed, that becomes an IC that has a fixed functionality. Okay, so you can always create, for example, an adder using a PLA. All you have to do is make the right connections, right? So we saw that adder was using some of the inputs, right? The sum and like suppose you have A, B and C, the inputs and the outputs has to be connected somehow. So just that you have to do a truth table and see that what are the mean terms that needs to be connected. Okay, so for example here I have the first one is that A bar, B bar, C bar. A bar, B bar, C bar unfortunately does not occur in any one of the sum of product expressions, right? If you remember what the sum of products expression was, it was something like the sum of this, right? A bar, B bar, C plus A bar, B, C bar, this thing, right? So you take these four things and put them together. Okay, so that is how you can program that. So it could be a generic piece of device, a PLA, which could be programmed as a full adder. And not only that, this is a full adder, you can always create a 32-bit full adder, for example. Okay, so ideally your computer does not contain a full adder that adds single bits, not a very useful thing to have, right? You typically want to scale this entire thing up. So you have an array of A, not just AI, it should be A1, A0, A1 dot dot dot, it should be B0, B1 dot dot dot, similarly for the carries, right? And every such thing has to have an individual full adder of its own, right? So sum is also not just SI, it is going to be some S0, S1, S0, S1 dot dot dot. Similarly, the output carry is only 1 bit, of course. The intermediate carries are fair in the intermediate circuits, but if you have a overflow, right, that is called a carry out, this is just going to be some carry out. Okay, so the point here is that adder is an example that I gave, but it could be any circuit, any complicated circuit, any kind of a logical circuit should be implemented using a PLA, can be implemented, right? And you can start debugging that, you can see what is going wrong and go through that phase of design. Once you fully understand that this is a foolproof design, you can carry forward in, you can go forward in actually manufacturing that particular circuit. Okay, so any logical function we wish to implement could be accomplished with a PLA, which is called functional or logical completeness. Okay, so which means that you can define this set of all the different functions and their inputs and outputs, they should belong to the same set, right? So everything should be possible to do. And PLA consists of only AND gates, OR gates and NOT gates. NOT gates are nothing but inverters. We have to program the interconnections, okay, based on the intended logic, and you all know the SOP. As I told you that SOP is typically more commonly used. You can always use the dual form or the product of some form, but that is more of a to show that these aspects also exist. You can stick to only one thing, and SOP makes more sense because we typically use the positive logic for 1 and negative logic for 0, right? A inverted is treated as 0 where A is treated as 1, right? Which is the other way around for POS, which is a little bit confusing, but that is just for knowing the difference in between POS and SOP. But once we do all these designs, you can stick to either one of them in which you are more comfortable in. Okay, it should lead to the same circuit, it should not lead to a different circuit. The set of AND or NOT gates is logically complete. It's very important to understand that, because we can build a circuit to carry out specification of any truth table. Okay, the reason is very simple. You need to have only the AND gate and the NOT gate to create any mean term, just that the AND gate size will vary depending on the number of variables, and you can club together multiple mean terms using the OR gate. So practically you can make anything possible.